Welcome to this video on how to run a linear growth curve model as a multi-level model in the Mplus software. My name is Christian Geiser. On this channel I present weekly statistics tutorials, usually related to multivariate statistical methods such as structural equation models, multi-level models, or latent class models, and often I discuss issues in the Mplus software. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including my weekly newsletter and other videos and workshops. So in this video here, I want to show you how you can specify and run a linear growth curve model in the Mplus software within the multi-level modeling framework. As you may know, linear growth curve models for longitudinal data can be fit as either structural equation models, meaning factor models, special types of confirmatory factor models, or they can be run as random coefficient regression models within the multi-level or hierarchical linear modeling framework. And so that has specific advantages or disadvantages, whether you use factor analysis or you use multi-level modeling. I will discuss this in a separate video. Here I just want to show you how this is done in Mplus when you choose to run such a model as a multi-level or random coefficient regression model. So you can see here I have my Mplus syntax, and in my variable names list I have just three variables: an ID variable or person variable that indicates the people, so say the level 2 units. In this case, we have time points nested within persons. So the ID variable, so say, is the cluster variable and is therefore listed here in the cluster statement because that identifies how the observations are nested. In this case, time points nested within individuals. The time variable then is my within level or level 1 predictor variable. So I am using time to predict my individual scores on my outcome variable y, because the y scores may vary as a function of time because there might be change over time. So growth, so to say, people might grow over time or decline over time with regard to, for example, ability scores or depression scores or other kinds of constructs. And so I'm using time as a level 1 predictor, so to say, in this model, and I'm assuming that there's a linear effect on time. So it's a linear regression model with random coefficients that can vary between people because people can have different intercept values, meaning different starting values or values at time 0, time 1, and they can have different rates of growth, different amounts of change. And so therefore it's a random coefficient regression where the intercept and slope values can differ between people. So in Mplus then I include my outcome variable as a under use variables and the time variable. The ID variable does not have to be listed under use variables because that is a variable with a specific function in the Mplus terminology, and so this only serves as a cluster variable. It's not a variable in the model, and so therefore it does not have to be listed under use variables, but it has to be listed as a cluster variable because otherwise Mplus wouldn't know how the nesting or what the nesting of the observations looks like. I also have to specify that time is a within variable, meaning this is a predictor that acts at level 1. You could also have level 2 predictors, so between level predictors, if you wanted to, for example, predict the intercept or slope factors. For example, look at whether there are age differences or gender differences or any other person level or time invariant covariates, then you would specify them under between. So you would say between equals and then your level 2 predictors or covariates. Furthermore, we have to specify as the analysis type 2-level random because this is a 2-level regression model, a random coefficient regression model with random slopes, because we typically also think that the linear growth factor or slope factor should have a random coefficient, meaning it should vary between people. The slope values because some people might change more than others. And so in order to allow for individual differences in the growth rate or rate of change over time, we specify the slope as a random coefficient. In the terminology of structural equation modeling, we would say it's a slope factor with a variance and a mean. Now, in the model statement, we have a statement for level 1, which is in the Mplus terminology called the within level. So we specify percent within percent to indicate what model holds at level 1. And that's our random coefficient regression model. You can see here that I have a statement that says y on time. So that is my regression of the outcome variable on time. And then before that, I have the symbol here that indicates a random slope. So this symbol is the Mplus symbol for defining a slope as a random coefficient. And then you give it a label. In this case, I just simply called it slope. You could also call it linear or something like that, or growth or something, depending on how you want to name your slope factor. So that's all we have to specify at the within level. The intercept of that regression is automatically seen as a random coefficient by Mplus. So there's nothing that you really have to say about the intercept factor. It will automatically be in the model with a mean and a variance estimate. The level 2 model in this case is very simple. So that's the between statement here that refers to what's going on at level 2 in this model. And so in this model, I don't have any predictor variables at level 2, but again, we could have that. So we could regress the slope, for example, on a level 2 predictor, and then that would be part of the between statement as well. In this case, it's, so to say, an empty model at level 2. There's not a predictor variable at level 2. And the only thing that really we have to, or we should specify, is that we want to allow for a covariance between intercept and slope. And that's done by saying slope with y. So y refers to the random intercept at level 2, and slope is the random slope that we just defined here in the within statement. And so slope with y tells Mplus that we want to allow for a covariance between the intercept factor and the slope factor in this linear growth model. Now, how does Mplus know that this is a linear growth model and not, for example, a quadratic growth model or other nonlinear growth model? It knows that because we have only time as a predictor here and not time squared. So we could also define time squared and include that as an additional predictor. So then we would have a quadratic growth model. But in this case, we only have time, so it's only a linear model or a linear linear growth model. And so therefore, so that's what we get. So let's take a look at what we get here in the output file in Mplus when we run this model. You can see that we get a warning message that says one or more individual level variables have no variation within a cluster for the following clusters. So the cluster or person number 140 and the cluster or person number 155, they don't have variation over time. So that could happen when a person doesn't change over time. Now, this is kind of unlikely, right? So you should always, that there's not at least a little bit of change, because there's also measurement error involved. So there should be a little bit of variation that is just simply random variation due to measurement error. And so if we find something like that, then we should check our data file and see, does it make sense that these people don't have any variation in their scores across the however many measurement occasions you have. So you want to check that if you get a message like this. In this case, this is a simulated data set, so there's or artificial data set, so it's not an issue. But whenever you get such a message, then you want to check that there's no error in your data. So here we have now as the number of observations 1940, and notice that that's not the number of people, but that is, so say, the total number of data points. So the number of time points times the number of people, so to say, times the number of clusters, because the people here are the level 2 units, and so they are listed as clusters, and the number of observations is the number of time points times the number of clusters. So that's important to know. Where do we find the number of clusters? That's given here under summary of data, and that gives you the number of people. Yeah? So we have 485 people, and we have 4 time points in this example. And so we have 4 times 485. That's our total number of observations, which is given here. Furthermore, we get the intra-class correlation coefficient by Mplus. So that indicates that there's substantial dependency here in the data, which makes sense because those are the same people that were assessed on multiple time points. So there's a significant stability over time in the inter-individual differences. That's typical for longitudinal data when you have a construct that has a trait component, that there's stability, so say over time in these scores. And so that's reflected here in the very substantial intra-class coefficient, correlation coefficient, that shows you that there's substantial consistency across, or stability across time. Model estimation terminated normally, which is always, or is a good sign. And we get some fit statistics here. The information criteria and the log likelihood value. Notice that you get fewer fit statistics for a model like this than you would get if you ran this as a confirmatory factor analysis model, because then you would get a chi-square test of global model fit as well as other fit statistics. So that's one downside of running this model as a multi-level model. Otherwise, you should get the same or very similar results because it is the same model. Under model results, you can see that in the within level, we get the residual variance for y. That's the only parameter that is estimated at level 1, because the other parameters are all relevant, or for the random coefficients, the relevant parameters are estimated at level 2. And so that's the only thing that we have at level 1 is the random variance, the random effect, the error variance here. So that's our measurement error variance. And then at the between level, we have, first of all, the covariance between intercept and slope that is estimated here. You can see it's negative and it's statistically significant. So there's a negative relationship between the intercept factor and the slope factor. That's often something that we find in longitudinal data, that people with initially higher scores change less than people who have, or grow less than people who have initially lower scores. So people with lower scores have more room to improve, so to say. That's often the reason why we find a negative correlation. Notice though that this is not the correlation, this is the covariance, because this is the unstandardized solution here. And that's one other advantage with structural equation modeling in Mplus, that if you ran this as a confirmatory factor analysis model, you would get the standardized solution as well. So here within the multi-level framework, you don't get the standardized solution unless you use a Bayesian estimator. Furthermore, we get the mean of the intercept factor. So that's the average initial value, so to say. And we get also the mean of the slope factor. So that's the average growth rate. And so you can see that here on average, there was a decline in this construct, and the slope factor mean is statistically significant, which means that on average, there was a significant decline over time, linear decline by this rate. We also get the random effects here for the growth factors. We get the variance of the intercept factor, and we get the variance of the slope factor. So those show to which extent individuals differed in their initial scores and in their growth rate. So how much, so say, how different were people in how much they changed. That is indicated here by this slope factor variance. So that's what you get for a multi-level in the multi-level output for a linear growth curve model in Mplus. Now you may ask, why should I do this since it has disadvantages? I could also run this model as a confirmatory factor analysis model, and I have a video on that too here, by the way, on this channel, where I show how you can run a model like this as a factor model. But it does have certain advantages in some situations to run this as a multi-level model, and that is when you have many time points and when you have a lot of missing data, then it can become tricky to fit this as a factor model. Also, when you have imbalanced time points where people responded at very different times and there's unequal spacing between time points within individuals and or between individuals, then it becomes tricky potentially to run this as a factor model, and then it might be easier to account for those complications in terms of a multi-level model. So it does have its place. In some situations, this is more practical than running this as a factor model. I hope you found this video useful to get started with multi-level modeling of longitudinal data in the Mplus software. If you did, then please subscribe to this channel. Don't forget to hit the like button, leave a comment in the comment section, and check out the description for additional resources, and I'll see you next week.